Before we answer that question, we'll need to briefly go over the visible light and how we actually see our environment, both of which should be pretty familiar to those of you who've done any sort of science back in school. You see, visible light is the only part of the electromagnetic spectrum we can actually see. The human eye has evolved to detect wavelengths of 380 to 700 nanometers long. As we know, light always travels in a straight line, unless it hits a denser material. In that case, it will slow down, leading to the wavelength to be decreased, and it will change direction at the boundary. This is refraction, and that is what causes light to bend, and we'll come back to this when we're talking about lenses later. Light waves from unfiltered sources can have multiple different planes of oscillations, one going up and down, one going light, so on and so forth. Because light is a transverse wave, which means that the energy is at a perpendicular angle to the oscillations, like that. Additional perpendicular means it can be polarized. Polarization means that the wave will only oscillate along a single plane. Here, I have a model of a pinhole camera. Yes, it was made pretty quickly, but it gets the job done from what I'm about to show you. You see, this small hole in the front is where light comes through, and it's called the aperture. It has to be small, otherwise you'll get lots of scattered light from different directions hitting it in the cruiser. We'll get to that later. Spoilers. And here is the viewfinder, and inside there I have a little sheet of paper for the light to land on. But back in the early 20th century to late 19th century, this would actually be photosensitive film that would react to what light hit it. This isn't a history lesson though, this is physics, so we're going to carry on. Going away from cameras quickly, when light leaves from the sun, it can do two things once it hits an object. It can be absorbed or it can be reflected. The only reason why this plant is green is because it's absorbing the wavelengths that aren't 495 to 570 nanometers, which, in case you didn't know, was the wavelength of the colour green. So it's only reflecting that range of wavelengths into my eyes, and I can see it to be green, unless you're colourblind and you don't see it. But that's a different story. That's more biology, if anything. If we apply that concept back to the camera, as I briefly mentioned earlier, all that reflected light will go through the small hole to be focused. If the hole was any bigger, like I said earlier, too many waves coming from different angles would make this final image too blurry. We have a single point here for the aperture for only a select few wavelengths to come through, only from one angle. If it were any bigger, you'd have multiple different wavelengths from different angles scattered all over the place. That's it. Right, we can fast forward a century and a bit to talk about the modern camera. We'll go over three main components: the lens, the aperture, and the sensor. To put it simply, the lens is responsible for focusing all those light waves into the sensor. Zoom lenses often make use of convex and concave lenses in pretty complex arrangements, a lot of X's there, to adjust the zoom and the focal length of your image. In case you didn't know, the focal length is just the distance at which those light waves will focus. Telephoto lenses make use of the biconvex model in most cases, and as the name suggests, this has two convex lenses with one concave one in the middle of them. If you wanted to zoom in, that concave lens would be pushed further towards the sensor, which would spread out the light waves a bit more, and if you wanted to zoom out, pushed closer to the sensor, which would really move the light waves in. I'm not doing it though with my hands. You may be wondering, but surely that's going to make the final image out of focus when it hits the sensor. Well, yes, but that's what the final convex lens is used for. That convex lens is responsible for focusing all of the remaining light that actually hits it. So if it's spread out, yeah, that's how you get this image. No! You may be wondering, but surely that would cause the light waves to be on focus when it hits the sensor. Well, yes, but that's what the final convex lens is used for. That pushes in all of the remaining light waves that hit it, and it focuses it onto the sensor, and that's why you get less of the image when you zoom in. It's pretty simple stuff, really, actually. There's a reason why it's so simple. It's because there's an oversimplification of all of the whole thing. In reality, your traditional zoom lens would have a lot more complex arrangements of these smaller lenses I just talked about. It's quite hard to put into words, so a diff should be here. When you zoom in with a lens, you'll notice the background behind you will be out of focus. The more you zoom, the more out of focus it will be. As you can see, I'm using a bigger zoom lens here, so we've got a bigger focus out here. I'm actually really far away from the camera. It's whatever. This is called bokeh, and it is a result of those unfocused light waves hitting the sensor and creating little circles of coolness. The shape they are depends on the shape of the aperture, and bokeh is caused by a shallow depth of field, which comes about when a wider aperture is used. Wider apertures let in more light while also decreasing the distance between the nearest and farthest object that can be focused at, also known as the depth of field. So, for example, I'm out here, I've got massive focus back here, but if I zoom in and out, you may notice I might be slightly more focused. I'm slightly less focused if I do that, as opposed to if I just sat here. Yeah, that's the depth of field. It gets more sensitive as your aperture gets wider. This means that it would be better to shoot wide landscapes with smaller apertures, but the same thing could not be said for shooting photos at night. Now, we've talked quite a bit about aperture throughout the video, but I just wanted to quickly go over f-stops or f-numbers, which are more specific ways of expressing aperture sizes. The f-stop is the ratio of a lens's focal length to the aperture diameter, and it's a good indication for the amount of light going through the lens. Right, to recap, larger apertures mean shallower depths of field, which are ideal if you want some background blur to your photo or video. They also let in a lot of light, whereas smaller apertures causes wider depths of field, and it's more suited for wide landscapes. But that's like the sensor. Last thing, it's the sensor. This is probably the simplest part of the whole camera. It's initially being photosensitive film, as previously mentioned earlier. That would have been processed to be a proper image, so now it is fully electric. To put it simply, the modern image sensor works by converting the focus light waves into varying electrical signals based on their intensity. These signals convey information like colour, stuff like that, and translate it into a digital image. And that's pretty much where the physics and cameras end. From there it just devolves into paths of chemistry and computer science. You've got chemistry for film, computer science for sensors. But yeah, this has been my attempt at explaining how cameras work with physics, and in my opinion, it's been a pretty successful one.